Hello everyone and welcome back. Today we are tackling a classic and challenging problem on Leetcode, find median from data stream, problem number 295. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. Imagine we are receiving a continuous stream of numbers one by one. Our task is to build this MedianFinder class such that calling its constructor initializes the object, and then it should support two operations. First, an addNum method adds a new number from the stream to our data structure. Second, a findMedian method returns the median of all elements so far. Answers within 10 to the power of -5 of the actual answer are accepted to account for potential floating point precision loss. If you are curious about why floating point numbers can lead to precision loss and why direct comparisons of float might not work, please check out this short video. Will 3 times 0.1 equal to 0.3 in Java, or will it be false? Now, resuming to the problem, the median, as you might remember, is the middle value in a sorted list of numbers. If the list has an odd number of elements, like we have here, the median is the single middle element, which is 3 here. But if the list has an even number of elements, like this one, then the median is typically the average of the two middle elements. So here we have 2 plus 3 by 2 equal to 2.5. Let's see it in action with an example. We start with an empty MedianFinder object. Next we add number 1 and then 2. Then findMedian is called, and since the list size is even, the median is the average of the middle two and is equal to 1 plus 2 by 2 equal to 1.5. Next, we add 3 and again find the median, and since this time the list size is odd, we return the middle element 2 as the answer. Alright, let's dive into the most straightforward or naive way to approach this problem. The simplest idea is to append the number when the addNum method is called, but when findMedian is called, we sort the list and retrieve the middle one or two elements based on the parity of the list. That is, whether the number of elements in the list is odd or even. This way, addNum has a time complexity of O of 1, but findMedian has a time complexity of O of n log n. For example, when we add the numbers 5, 15, 1 and 3, and then when findMedian is called, we sort the list and get the following list. And since the list has an even number of elements, we return the mean of the middle two elements, which is 3 plus 5 by 2 equal to 4. Another naive approach is to make the addNum method a bit expensive. We can insert elements into the list while keeping it sorted. So, when the addNum method is called, we find the insertion point in the sorted list using binary search, which takes O of log n time. Then shifting elements in the array takes O of n time. This makes the time complexity of addNum method as O of n plus log n. However, findMedian is now O of 1, as it simply retrieves the middle elements based on parity. For example, first we add 5 to the list and the list is already sorted. Next we add 15 at its insertion position 1 and the list remains sorted. Then we add 1 at the insertion position 0, moving existing elements to the right. Finally, we add 3 at the insertion point 1, shifting elements to the right. And when findMedian is called, since the list is of even length, the median is the average of the two middle elements, which is 3 plus 5 divided by 2 equal to 4. The bottleneck in our naive solution is the repeated sorting. Every time a new number arrives, we are essentially reordering the entire collection, which takes O of n log n time. If we have a million numbers, that's a lot of work just to find one or two middle elements. But do we really need to have the entire list sorted? And the answer is no. We just need to efficiently know what the middle elements are. And if we look at these two middle elements closely, assuming the list is even, this middle element is largest of all the elements on its left, and this one is the smallest of all the elements on its right. And these two elements will lead us to the answer. In case of odd number of elements, we just pick one of them. So, we need a data structure that can quickly give us access to the smallest elements and the largest elements and keep them somewhat ordered without the overhead of full sorting. And what data structure is great at giving us the smallest or the largest element quickly? You would have guessed the answer by now. It is heaps or priority queues, because in heap, say max heap, getting the max element takes just O of one time, and adding the element and removing max element takes O of log n time. So here we need two heaps to maintain the numbers in a way that the median is always readily available. For the numbers on the left, we create a max heap called small nums. This heap will store the smaller half of the numbers. Because it's a max heap, its root will always be the largest number in the smaller half. Similarly, for the numbers on the right, we create a min heap called large nums. This heap will store the larger half of the numbers. Because it's a min heap, its root will always be the smallest number in the larger half. Our goal is to keep these two heaps balanced, ensuring two key properties. Every number in small nums is less than or equal to every number in large nums. And to efficiently pinpoint the middle elements, the sizes of the two heaps should be nearly equal, differing by at most one. Our balancing strategy ensures that if the total count is odd, small nums max heap will always hold that single extra element. Now for the find median method, if we maintain these properties and if the total count is even, the median will be average of top elements of both small nums and large nums heaps. But if the count is odd, the median will simply be the top element of small nums heap. And since this method only involves peaking at the top of one or both heaps and potentially performing a simple arithmetic operation of addition and division, the time complexity is an impressive O of 1. Now, let's see how the addNum method maintains the two properties. Initially, both heaps are empty. First number we are adding is 5, and every time we add a number, it involves 3 key steps. The first step is to place the new number into one of the heaps. And here which heap should we choose? Well, it's a design choice. For our walkthrough, we'll always add the new number, which is 5 here, to the small nums max heap. However, this might break the crucial property that all elements in small nums heap must be less than or equal to all elements in large nums. Just adding 5 to small nums could break this. For instance, suppose small nums already had number 1 and large nums had 3. Then, if we added 5 to small nums max heap, it will become the root and it is greater than 3 in large nums heap, violating the property. To correct this, after adding to small nums, we immediately move its largest element, that is, the root, to large nums heap. So, we move root 5 from small nums to large nums. This elegant pass-through ensures the property is always maintained. This step takes O of log n time, as removing the max element from small nums max heap and adding to large nums min heap both take O of log n time. So while this fixes the ordering problem, it might unbalance the heap sizes. Our strategy is to keep small nums either the same size as large nums or one element larger. since small nums is now smaller, we move the smallest element from large nums, which is 5, back to small nums. This rebalancing also takes O of log n time. Thus, the overall time complexity of addNum method is O of log n. This three-step process ensures both our properties, the value property and the size property, are always maintained. Now let's continue with the rest of the example. Next, we add 15 to small nums max heap and it becomes a new root. We move this root value to large nums, and since the heap sizes are equal, there is no need of rebalance. Next, we add 1 to small nums and we move root of small nums, that is 5 to large nums. And now, since small nums heap is smaller, we move root with value 5 from large nums to small nums. And at this point, if findMedian is called, median will be top of small nums, which is 5, as small nums have more elements than large nums. And finally, let's add 3 to small nums. And again, we move the root 5 of small nums to large nums. Now, 5 becomes root of large nums. And this time, heap sizes are equal, so no need to rebalance. And next, when findMedian is called, median will be average of roots of small nums and large nums, as the heaps are of equal size. So, median will be equal to 3 plus 5 by 2 equal to 4. Let's now walk through the code for our optimal 2-heap solution with Java code on left and Python on right. In Java, we use priority queue. For our small nums heap, which needs to be a max heap, we pass in collections reverse order comparator to its constructor. Large nums is a standard min heap. Python's heap queue module only provides min heap functionality. To simulate a max heap for small nums, we'll store negated values. When we retrieve from small nums, we'll negate the value back to get the original number. Now, let's look at the addNum method, which is where the core logic happens. We first add the new number num to the small nums heap. In Java, we add elements using the add method, and in Python via heap push. Also in Python, remember we negated to maintain the max heap property. Immediately after adding, we take the largest element from small nums, which is its root, and move it to large nums. This ensures that all elements in small nums remain less than or equal to all elements in large nums. To remove the root element, we use poll method in Java and heap pop method in Python. Next, we perform the balancing step. If after the previous step, large nums ends up with more elements than small nums, then we take the smallest element from large nums, that is its root, and move it back to small nums. This ensures that small nums is always either the same size as large nums or one element larger. Finally, let's look at findMedian method. If small nums has one more element than large nums, it means we have an odd total number of elements. In this case, the median is simply the largest element in the small nums heap, which is its root. In Java, we use the peek method to access the root element, while in Python, we get the root value using index 0. However, if both heaps have the same number of elements, then we have an even total. The median is the average of the largest element in small nums and the smallest element in large nums. We sum their roots and divide by 2.0 to ensure floating point division. And that's the elegant 2-heap solution. It keeps our data organized just enough to find the median efficiently. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.